Okay, so we will have now the second talk by Tom Hales, who Cedric already introduced partly. So Tom Hales, after proving the Kepler Conjecture, started a project of formalizing it, the FlySpace project, and this is mainly, I think, what you will talk about.
Thank you. It's an honor to be here today and to speak a little bit about my work in discrete geometry and efforts to formalize the project. I want to start by thanking my many collaborators and sources of inspiration on this project. Point out especially 2 graduate students and then postdocs who have worked with me very long on this project, Alexei Soloviev and Huanglei Trung. I'd like to thank the organizers as well and thank them for putting oranges in the middle of Paris here. If you look at the center of the diagram, we have a sphere packing. And once you've studied packings long enough, you start to see them everywhere you go. I want to zoom in on this picture a little bit and talk about arrangements of packings in 3 dimensions. So the problem is a very simple one. What arrangement of balls or oranges or fruit is the densest possible in the sense that it fills the largest possible fraction of space? A question I often ask students is, well, okay, so the answer is a pyramid. Do you think it's a square pyramid or a triangular-based pyramid? And about half of them will say one, and the other half will say the other. And of course, the answer is that both are the same. One is just reorientation in space of the other, as you see in this picture. We've got a square-based pyramid. And when you put 2 of them next to each other, so I've got a little diagram here on the left that shows that if you have 2 square-based pyramids, you can fit a triangular-based pyramid in between the 2. You see that they fit seamlessly together, so they're really the same structure, one just oriented differently from the other. So the thing I want you to get out of this picture is what is really the first question that was asked about sphere packings. And that is, so if we look at this particular pyramid, we have one on top, and then we have a square below it. And then we have, if we fill in the middle, then we've got a layer of 9, so 3 squared below that, and then 4 squared, and then all the way down to the bottom, a layer of 5 squared. So we can easily add up how many are in the pyramid. But suppose we have a triangular-based pyramid. What's the formula for the number in the pile? And this actually goes back. Let's see if I can. It's not working for me here. This goes back to about 500 AD. Sanskrit source says, for a series with a common difference in first term of 1, the product of 3 terms successively increased by 1 from the total, or else the cube of the total plus 1 diminished by its root divided by 6 is the total of the pile. So if you translate that into modern mathematical notation, you get these 2 formulas for the number of cannonballs in a pile. One's n times n plus 1 times n plus 2 over 6. And the other is n plus 3 cubed minus n plus 1 over 6. So after seeing this, I wondered, how in the world did they think of this solution in the year 500 AD? So this is the answer that I came up with. First, if the answer is going to be a cube, then maybe you'll want to make the balls into cubes to arrange them. And then let's put them in align them as I've shown. And then if there's a 6 in the denominator, maybe we should take 6 of these pyramids and try to fit them together into the arrangements, into the numbers as given. And so if we have n plus 1 cubed minus n plus 1, that's taking a cube of size n plus 1, subtracting out the diagonal, and fitting together exactly 6 of these pyramids to make the formula. And the other solution is to put them together without any gaps, so that the dimensions will be n times n plus 1 times n plus 2. And so we can put them together these two different ways and derive this old formula. Now, this isn't the only time this problem was solved. Again, in about 1590, the mathematician, scientist Thomas Harriot became interested in this problem at the prompting of Walter Raleigh. And he too came up with a solution to the problem. What he did is he made a little triangle. Starting in the row going down the diagonal to the right, we're going to make zero-dimensional packing. So there's just a sphere, a sphere, a sphere, a sphere, but there's no dimensionality to it. Going down the second, we're making one-dimensional packings. So I put 1, and then 2, and then 3, and then 4, and then 5, going on down. And then I start with 2 dimensions. I put 1, and then I take the 2 above, I take the 1 and the 2, and I put them together to make the 3. I take the 3 and the 3 and put them together and to get the 6. And so in every case, we take the 2 entries above it and add them to get the arrangements together to get the one below. And what you see from this diagram then is that the formula should be precisely a binomial coefficient, an entry in Pascal's formula. So this is the way that Harriot derived the formula. The density can be calculated from this picture. So I've removed everything but the parts of spheres that lie inside a single cube. And there are at the corners an eighth of a sphere at each corner, so we get 8/8 there. And then we have half a sphere at each face, so we get 6 halves there. So we get a total of 4. We get a total of 4 spheres, each of volume 4 pi over root 3. The edge of the sphere of the cube, as you see, is square root of 8, and so that gives the density of pi over the square root of 18, or about 74% of space. Kepler asserted that the face-centered cubic is the best possible, but it's not the only one. So here's a picture of a stack in what's called the hexagonal close packing. Normally, when you make the pyramid, the oranges would come straight down, but you see that the row underneath here has been rotated to give a different arrangement, the hexagonal close packing. And since they're both built on hexagonal layers, they have the same density. You're just shifting the different layers to get different arrangements with the same density. So here's what Kepler did. He wrote a booklet in 1611 called the Six Cornered Snowflake. In it, he said that the face-centered cubic, he described the arrangement and then said it will be the tightest possible so that in no other arrangement could more pellets be stuffed into the same container. He was apparently inspired to think about this problem while crossing a bridge on a cold, snowy night, and as he started to look at the snowflakes come down, he started to wonder, why do snowflakes have 6 sides? As part of those reflections, he started to think about other naturally occurring numbers. 6 comes up also in the bee's honeycomb. He thought of density as he looked at a pomegranate and thought, well, perhaps density is the factor causing arrangements to be the way they are. So if you look at the honeycomb, as Kepler did, the base is got 3 rhombic facets. And if you cut off the sides, so we've got 6 sides, but if you cut them off so they're also a rhombi, then you can put 3 more rhombic facets on the bottom, and what you get is what's called a rhombic dodecahedron. And because the honeycomb cells fit together, these rhombic dodecahedra also fit together, and they give a tiling of space. And if you put congruent balls inside each of these rhombic dodecahedra, you get exactly the face-centered cubic packing. So this is the line of reasoning that Kepler used to come up with the original conjecture. So long history short, this is the oldest problem in discrete geometry. Became part of Hilbert's 18th problem. It was finally solved by a graduate student from Sam Ferguson and me in 1998. The proof was about 300 pages long and relied on very long computer calculations. I was pretty exhausted at the conclusion of this and turned it over to the referees thinking I was done with it, but boy was I ever wrong. The process took much longer than I expected. I should have known, because this is what the proof looks like. This is from the original 1998 proof. It's got just pages and pages of long systems of inequalities that go on for a very long time. And the exact values of all of these constants have to be just right for all the equations to fit together to give the proof. And so, you know, naturally, I thought that the referees would just read the computer code to check that the proof was correct. But as time went on, I became more and more pessimistic about whether this would ever happen. In fact, I received a referee report from a referee who said, as a matter of pride, that he does not read computer code. And there was a conference for the referees when this was first submitted, and they gave very good indications that it should be published rather quickly. They said they were 99% convinced that it was correct. But as time went on, the referees became exhausted. At one point, I received a letter from an editor who basically said, look, we'll publish it as soon as you convince us that it's correct. Well, traditionally, it's the mathematical paper that is supposed to do the convincing. But this I eventually saw as an opportunity. So in 2001, I started to look towards the formal proof community as a way to make an end run around the referees, not just for myself, but as a hope of future technology that will make it possible so that someday in the future, referees will not have to deal with the tedious details of checking the correctness of proofs, but instead they can concentrate on the significance of the results. So I attended the International Joint Conference on Automated Reasoning, met up with a number of the experts in the field, and a couple of years later announced a project called the FlySpec project, whose purpose was to give a complete formal proof of the Kepler conjecture. So what this means in general terms is that you put the axioms of mathematics into a computer. Georges Gontier just talked about a proof in the Cox system. I'm using the whole light system. Whole stands for higher order logic. It's again a system, a foundational system based on in this case, a very simple type theory. And the project was to check every single step of the proof, both the 300 pages of text and also the long computer calculations that were part of the proof as well. So the first big success on this program was by Tobias Nipkow with a student, Gertrude Bauer. They wrote a paper called FlySpec 1, which completed the verification of one of the three major computer programs that gets used in the proof. So this was a program that does a classification of planar graphs with certain properties, and there were a couple of thousand graphs that come up in this classification. So let me show you the whole light system. I was coming to this as a pure mathematician without earlier experience in formal proof systems, and I had to decide which system to use. I got various recommendations, but I eventually turned to whole light. So one thing that I really liked about it was that this one is a very simple formal proof system. So the trusted kernel that implements all of the axioms and the types and the terms and what theorems are and everything, I can fit on 3 slides. So this, and this, that gives the entire trusted kernel of the system. So this is very cleanly implemented code. I was able to read over it and develop a degree of trust that, okay, I understand what this computer code is doing. I understand mathematically how to model this in set theory or in higher order logic. So I see what it's doing. I know other logicians, mathematicians who have checked over this code carefully for bugs. And in fact, there haven't been any errors or bugs found in this for more than 10 years. So I believe at this point that it's a completely bug-free piece of code. And it's just 600 lines that we need to check. So I'll leave it to you now to see. But we just implement the type system, for instance. I don't know. I had to make it in a small font to fit it all in 3 slides. But for instance, the entire type system is contained in these 2 lines of computer code. So that's how simple the type system is. You'll hear a lot about types at this special program, but that's the type system for this system. Another thing that inspired confidence, this happened in 2006, is John Harrison did an actual proof of the correctness of the kernel inside itself. So this is a formal proof to get around Gödel type problems. He did 2 versions, one where he removed, a weakened version where he removed the axiom of infinity, and another one where he added a large cardinal axiom to give a stronger version, proving the ordinary version. But it checks not only the correctness of the underlying logic, but also the correctness of the implementation using a fairly good model of what the language is doing. So for my part of the project, my biggest effort has been in reworking the proof in such a way that it would even in principle be possible to do a formalization. With a lot of mathematics, when you read it, you realize that, well, this isn't something you could really formalize because it's too vague or just not enough details. And it really took a lot of work on my part to create a second generation proof that is something that I would be willing to sit down and try to formalize. And this happened at the same time. So the proof is about the same length. It's about 300 pages long, but it's really much more systematic in the way that it develops the ideas and goes into all the background theory of all the other facts that are needed that weren't included in the original proof. So one of the changes that I made is in the decomposition of space that gets used. So roughly speaking, different partitions of Euclidean 3 space, here I've illustrated with two-dimensional pictures for simplicity, but different partitions correspond to different ways of trying to prove the Kepler conjecture. So a couple of well-known partitions of space are given by, first of all, the Voronoi decomposition, where these points represent the centers of all the balls. And then if you associate with each sphere center all of the points that are closer to that center than to any other, you get the Voronoi decomposition. And then there's another decomposition with the same sets of points, but that's exactly dual to it. So every time 2 points, 2 cells share an edge, you connect those two by you connect the 2 points by an edge, and that's the Delaunay decomposition. And the bound on sphere packings that you get from this approach is about 75% density, and what you're trying to prove is about 74%. So you're off by about 1% when you use this approach. When you use this approach, you're off by just a few hundredths of a percent. It gives a bound that's extremely close to what you want to prove. But it seems that there was really no way to go any further with this approach directly. You get stuck a few hundredths of a percent away from your final goal. And so what you need are much more intricate decompositions of space to give a proof of the Kepler conjecture. And this is, so what I used eventually was the 3-dimensional version of this picture. And the original motivation was to somehow create a hybrid between these two pictures, putting triangles in certain regions of space and using the Voronoi cells in other regions of space. Intuitively, you want to put the triangles in areas where you have high density and the Voronoi cells in areas that you don't really care about so much and that have low density. And in the revised version, Marshall published a paper in 2011 that gave a revised decomposition of space that looks fairly similar to what got used in the original 1998 proof. But in terms of the rules describing the decomposition, it's much, much simpler than what we used originally. And so we switched over to this other decomposition of space in the revised proof. So something else that really helped as part of this project, we got an NSF grant, and I went on sabbatical to Hanoi in 2007, 2008. I came back in 2009. We organized an international workshop on formal proofs related to this fly-spec project. And a lot of people there. There was an incredible amount of just very good students and researchers who became involved in the project and have helped very much with the formalization. So this is what the formal statement looks like. We go now from pictures to formal text. The statement of the proof of the Kepler conjecture, we need to say what a packing is, and we throw away the balls and we just keep the centers of the balls, and we make the we make everything unit radius. So the points of the packing, if the balls don't overlap, have to have distance at least 2 from center to center. And so a packing is just a discrete set of points in Euclidean space such that no 2 points have distance less than 2 apart. And the statement then is just counting V is our packing, and we just count the number of sphere centers inside a large ball. And this number pi over the square root of 18 that comes up as the optimal density is the number here. Factor of r to the third comes up because of the size of the ball. And then we have an error term, which is of order r squared, so that as you go to infinity in the limit, you get a bound on the density of pi over the square root of 18. So to really verify this, you need to, what the mathematician needs to do in checking this is to look at the definitions to make sure that pi really is the number pi, that the cardinality really is the cardinality. So for instance, the number pi, we've got just the usual arctan formula for arctan 1 is pi over 4, and that's series is a theorem in the system, so you can just look at this and say, okay, pi really is pi. We didn't cheat on the density. And then there are other definitions as well, such as just what the metric is and what cardinality is, what finite sums are, what the absolute value is, and the square root, and so forth. So this, let me show you where we are. The project's not complete. We're getting close. So this is what we formalize in a single session. We've got 4 assumptions here still, unfortunately. Linear programming results, the nonlinear inequalities, import tame classification, restricted hypermaps or plane graphs, and then we have the proof of the Kepler conjecture. So the first 3 assumptions roughly correspond to the 3 big bodies of computer code that appear in the original 1998 proof. This 4th assumption is just, well, that's work in progress. I got an update over the weekend. That should be gone in a few weeks. But it's the step that's merging all of the different pieces from all of the different libraries. So I think within a few weeks, that particular assumption will be gone. And then I've got check marks by 2 of these assumptions because they have actually been completed as well. What I've said here is this is what we formalize in a single session of Holite. I told you that the first big success of our project was that Nipkow and Bauer did a formalization of the first major piece of computer code. They did this in a different proof system, Isabelle. And so now we've got pieces of the proof in 2 different systems. So what we have here is the translation, the word-for-word translation of their statement into Holite, introduced as an assumption in our system, proved in a different system. And that's unfortunate. We're looking for a student who's willing to merge this for us, but right now it's still straddling 2 different systems. And then the other check mark is by the linear programming results. Let me give you just a very quick overview of how the proof goes. You start with a sphere packing, and you want to show that it's worse. It's a proof by contradiction. You want to show that anything else is worse than the face-centered cubic or its variance. And what you do is you make a combinatorial, you make a graph for the local arrangement around each sphere, and this turns out to be a planar graph. And then you study the properties that this graph has to have. You make a long list of properties, and then this first computer program classifies all such graphs. And in the current version, there are about 25,000 graphs that come up as possible counterexamples to the Kepler conjecture. For each of these, you have a hard nonlinear optimization problem to solve of checking something about the density. This is taking place in high dimensions. Let's say we're working in nonlinear optimization problem in 45 dimensions. So I was going to draw this for you, but instead I thought, well, what does a 45-dimensional hard nonlinear optimization problem look like? And I said, well, this would look like something with lots of teeth and a fin. So that is what I put. And then you have a nonlinear optimization problem. That's the beast that you're trying to deal with. But since nonlinear optimization in general is NP hard, you want to replace this by something that's much easier to solve. So that's where the Shark Tank comes in. We use what are called linear relaxation methods. So instead of the original nonlinear domain, you relax it into a convex polytope. And there you can use linear programming techniques to study the maximum. And so once you've contained the nonlinear problem inside something linear, it becomes, so then we have about 50,000 linear programs to solve. And that part, the linear programming part, which is the part in high dimensions, has now been formalized as well. So this was part of Solovyev's PhD thesis, that he's done a complete formalization of all of these linear programs needed for the formal proof. So the part, in a few weeks, the part that will remain is the nonlinear inequalities. This is a very challenging part of the problem. In principle, so there's actually been 3 PhD theses written related to this part of the problem already. Roland Zoomkeller did nonlinear optimization. Victor Magron recently defended a PhD thesis. And Alexei Solovyev also did a PhD thesis, all sort of motivated by this problem of being able to formalize nonlinear inequalities inside a formal proof system. So in principle, Solovyev's thesis implements all of the code that we need to finish off this last piece. The only thing is we haven't tested it on the hard inequalities yet, so there could be some snags that come up. But we think that it should be merely a matter of running the computer for 10,000 hours now to finish off the rest of the proof. But I won't be terribly confident that there are no snags until it's actually done. So this is just a bit of a summary. 10,000 hour computation is what's left. The last few minutes of my talk, I want to just, I've been focused on this stack of oranges. Now I want to step back in the last few minutes and look with a little broader perspective of why all of this is important to me and hopefully to other researchers. If you go to Wiki, there's a list of long proofs. There are about 25 proofs on the list. Four-color theorem is on the list. Feit-Thompson is on the list. Kepler Conjecture is on the list. So there are 3 of these 25 or so long proofs that are being attacked by methods of formal proof. There are many other examples as well. My advisor is there, Langlands, for his work on Eisenstein series. Another of my advisor's students is there, Jim Arthur, for his work on the trace formula. Laforgue, somebody else in the Langlands program, is there for his work on geometric Langlands. But Harishchandra, Vey conjectures, many other. So what I see this all being about is extending the reach of mathematics. We've sort of hit a limit to what we can easily check by hand. And we don't want this to be the limit of what we can do in mathematics. But in future centuries, we want to go far beyond what we're able to do today. And I see formalization as being a very essential tool in making that come about. And so part of that is, you ask, how tall is a tall building? Well, that depends entirely on what your technology is. And the same with mathematics. How long is a long proof? That depends entirely on what your technology is. And by improving the technology, you can improve what it is that we're able to do as mathematicians. And going along with that in a similar vein is that there are now many proofs that are done by computer. So I've made a list. This is just sort of a list of things that occurred off the top of my head, but these are different conjectures that people came up with using computers, or different proofs that people have done by computer. And it's no longer just a matter of a couple of examples like the four-color theorem, but you talk to a lot of mathematicians who have computers as part of their proofs. And right now we have no standards whatsoever for the checking of computer proofs. It's just sort of the Wild West out there in terms of computer proofs. And what we really need, so I'm very much in favor of moving mathematics more to computers. But we don't want to do it in a way where we lose out on the reliability that we've had traditionally in mathematics. We want to do it in a way where we become actually more reliable than we were in the past. And that's possible with formal proof technology. So then, finally, if we look at this picture, okay, so we've seen that oranges are in the center of things. But if we look out here at the airplane passing overhead, we want to do certified software verification as well. And even though I come at this from the point of view of as a pure mathematician, we're reading all the time about big bugs that are causing huge problems. And part of my motivation in putting all of this effort into formalization is because I know that this technology is going to be very valuable for others to use as well. And if I can help contribute in some small way, then it will make the world and the business world much better in many ways. We read about all the different bugs, whether it was Knight Capital in 2012 that lost, $440 million in 45 minutes because of a software bug. Or, in 2013, we read about, the NSA undermining cryptographic standards because there was no real quality control on the cryptography. Or we go to 2014, we read about the Heartbleed bug that's been in the news so much in the past weeks. Let me just quote from the New York Times this weekend, business section, first page. Ideally, the open source volunteers check one another's work in a peer review system similar to what found in science, okay? So we've been talking today about the peer review system in mathematics, or at least in the nonprofit Wikipedia. Well, that's a pretty low standard. But since the Heartbleed flaw got through, members of that world are questioning whether the system is working the way it should. And again in the article, Raymond said the code-checking system had failed in the case of Heartbleed. Belivan, a Columbia professor, also questioned the system for vetting code. So here again and again, the issue that's coming up is that the systems that are being used to do these verifications are just not adequate for the magnitude or for the importance of these pieces of software code. And so I think that's another reason why this is all very important to develop. So I just want to conclude with a remark that I made in this paper on the FlySpec project. At the bottom here, in truth, my motivation for the project are far more complex than the simple hope of removing residual doubts from the minds of a few referees. Indeed, I see formal methods as fundamental to the long-term growth of mathematics. Thank you.
Thank you very much. So, questions? You can dare.
So basically, you said that you were changing the proof as you are formalizing it. You are now going to use Marshall's technique. Do you think this is happening a lot, or it's just a marginal aspect of your evolution as you formalize the proof?
So the question
is it important? Do you do a lot of improvements like that, or it's only marginal?
No, the improvements have been quite essential to the project. I've really spent most of my time working on improving the proof. And
so the formalizing process is a creative process in this sense?
Well, yeah, so I could also point out that I was able to solve some other problems in discrete geometry as a result of this revision of the proof. So it did lead to some new mathematics as well.
What is your plan to mix HOL and Isabelle?
Well, you know, there are some translations that have been made between the systems. McLaughlin had a translation from Isabelle to Holide, and there have been translations made the other way as well, but as far as I know, the translation from Isabelle to Holide isn't functional right now. Isabelle has had some updates, and this translation process hasn't survived the updates. So.
Oh, other questions? Okay, so maybe we move to the break.